Good morning, afternoon and evening to everyone, depending where you are. My name is Mamane-Logsdon. I'm a second year, going on third year PhD student in the Martins Lab at Imperial College London, and today I'll be presenting a collaborative piece of work we performed with the Belos Lab at the University of Southampton, and that work is titled AlphaRING-X, which is a software package designed for both the accurate but importantly interpretable prediction of missense variant deleteriousness. And I'm very excited to further present this at the ISMB ECCB 2025 conference in just over a week's time. So let's get stuck in. So just a brief introduction. We know missense variants can have variable impact on the protein that they affect. It can be neutral, it can be deleterious, but the problem is most are not labelled as either, which makes it very hard to know which ones to prioritise in research. And as a result, many different kinds of software tools have been made to predict the label, i.e. is it neutral, is it deleterious? And CAD is a very widely used example of these software tools. But the problem with tools like CAD, etc., is whilst being excellent and very accurate, sometimes their predictions can be hard to interpret, as you receive a score and sometimes also a label, but not a lot of mechanistic insight into how that prediction was made, that individual prediction, which can make it quite hard to then interpret and construct downstream experiments on in the laboratory. And to answer this problem, we've developed AlphaRING-X, which is essentially designed to be both an accurate and interpretable predictor of missense variant deleteriousness. So let's talk a little bit about how the AlphaRING-X pipeline works. So it expects a missense variant on the amino acid level. So we've just shown the substitution that occurs here on the amino acid level. We then pass this missense variant through a feature extraction phase. So using AlphaFold, for the wild type residue that is substituted, we get a piece of information known as PLDDT, which is the per local distance difference test. This is a measure of confidence, local confidence in structure for that wild type residue. But because for these different structure prediction techniques like AlphaFold, this tends to serve as quite a nice proxy for when structure is and isn't present, because these tools tend to be very good when structure is present, but not very good when structure isn't present. We also, at the wild type residue that is substituted, extract an piece of information called degree using a software tool called Ring, which plots residues in a protein as nodes. So it's taking the structure from AlphaFold and is connecting those nodes with edges, i.e. bonds, covalent and non-covalent, that it calculates, and the degree is the combined total of covalent and non-covalent bonds made by the wild type residue that is substituted. We also get delta delta G from fold X, so the change of Gibbs free energy caused by the residue substitution. And then finally, we have this in-house feature called RSP, relative substitution position, which goes between a scale of 0 to 1, and it tells you where along the protein from the N to the C terminus, N being 0, C being 1, where the residue substitution occurs. And we funnel these four features through an XGBoost classifier that we train using gold standard human missense variants from ClinVar. So our original data set was around 1,600 variants. We did a 80-20 split between between training and testing. We also did calibration in between. And essentially this gives you a score of 0 to 1 for how neutral or deleterious your missense variant is. So closer to 0, the negative class, neutral, close to 1, the positive class, deleterious, but you also have an ambiguous range between the two, a bit like how alpha missense does, and we'll get into that in a bit. But very importantly, this score is explained using these things called SHAP values, which I won't get into too much now, but essentially what they do is they can tell you the amplitude and direction of impact that each feature is having on your predictions. So the model has a baseline which is based on an average score it expects based on its training data, and the difference between the baseline and your prediction are your feature SHAP values. So this is a way to mechanistically understand how these four features are actually creating your prediction, which is very helpful. So now we can get into a few results. So when we did benchmarking using our test set from our gold standard missense variants from the ClinVar database, we compared AlphaRING-X, shown as just ARX here, to CAD, and when we looked at the area under the curve, AlphaRING-X got around 0.94, CAD got around 0.90, and when we did a bootstrap p-test, basically, these AUCs are mean values from bootstrapping several thousand times, and this p-test measures how often we got the higher AUC v-CAD, and the p-value comes out as under 0.05, indicating that we have displayed, at least in our test set, a statistically significant improvement over CAD. So we have better discrimination power when it comes to classifying, in this case, benign from pathogenic human variants. So you can think of the benign as neutral and the pathogenic as deleterious. We also wanted to see how precision in both the negative class, i.e. neutral variants, and the positive class, i.e. deleterious variants, on a sliding scale affected how many variants we could resolve. Different methods in this area, such as alpha missense, use 90% precision in both the negative and positive class to derive lower and upper thresholds to create not only a range where we can call neutral and deleterious variants, but also a range in between called ambiguous variants. So at 90% precision, we had an ambiguous range between the probability of 0.22 and 0.27. So that's a very tight ambiguous range, and this is reflected in the fact that we were able to resolve 95.5% of our test variants. So only 4.5% were ambiguous. The rest were either called as neutral or deleterious. So that indicates the performance of AlphaRING-X and how it's competitive with the current gold standards. But what's also very important to us is the interpretability. So I was talking about how we use SHAP values of features for mechanistic insight into our individual predictions. So on our test set, we wanted to explore how these SHAP values could explain the predictions we were seeing and maybe some overall patterns. So what we can see up here first in this box plot distribution is that we're just looking at the amplitude here, so not direction. The features which have the biggest impact on prediction, whether that's making it more, a smaller value, i.e. a neutral variant, or a larger value, i.e. a deleterious variant, are degree and PLDDT. So whether there is, loads or very few bonds being made, and whether there's a lot of structure or little structure, this information is particularly important in creating a variant prediction that is either more benign, neutral, or deleterious. And we can actually investigate that a bit further in this SHAP summary plot, which allows us to not only look at the amplitude, but the direction of impact that the different features are having. And we can see using this feature value here, which just tells us the intrinsic value of the feature, i.e., is degree a very small number, or is it a very large number, and so on. We can see the relationship that the size of these feature values have with impact on predictions. So here, I won't go through every possible conclusion, but some very interesting ones that you can see is that as more bonds are formed by the wild-type residue that is substituted, there is a larger SHAP value, i.e. it is pushing the prediction higher up, it is making for a more deleterious prediction, and vice versa in the opposite direction. And we see a similar story with PLDDT, delta G, but a different story of RSP. So what this tells us is that variants that are towards the end terminus or in the middle of the protein tend to be a bit more deleterious than those towards the C-terminus. So this is very insightful in telling us how our predictions are made, what causes a deleterious prediction and what causes a neutral prediction. But it's also interesting to use these to investigate why we're doing better than CAD and do a bit of a mechanistic investigation into that. So here we just have this a spread of our test set variance. This vertical line indicates a very common cutoff for CAD scores, CAD Fred scores, where above 20, i.e. the top 1% of most deleterious variants are considered deleterious, and values below 20 are considered, in this case, neutral. And here we have two lines to represent that AlphaRIng-X has a upper and lower threshold and an ambiguous range in between. So this is about 0.22 and this is about 0.27, as I said earlier. And what's quite interesting is the bottom right here that you want to focus on. We are, and as is clearly shown here, able to call a lot more neutral variants as neutral compared to CAD. There are 17 instances in our test set of around 180 where we are correctly calling neutral variants neutral, but CAD is not. And this is where our improvement it comes from. And when we actually look at the amplitude of effect that different features have in just these 17 variants, we can see PLDDT jumps over degree in terms of the size of the impact quite massively, but degree does increase a bit too. But delta delta G and RSP stay about the same, which is already telling us that our ability to get good predictions is large in these 17 variants is largely driven by PLDDT and degree. And when we look here, we can see the predictions made. All of these different predictions, the PLDDT value was quite low, i.e. there's low local confidence in structure, which again serves as quite a nice proxy for lack of structure whatsoever, and a quite perhaps presumptive conclusion that we need to investigate more is that we are able to effectively make predictions of missense variant deleteriousness in not only structured regions of proteins but also disordered regions. So you can see these variants tended to have low degree values that the wild type residue has substituted, and you can see delta delta G and RSP look similar, a similar pattern, but just less and less important. So yes, to summarize, we have developed this tool called AlphaRIng-X. It's both an accurate and interpretable predictor of missense variant deleteriousness. We seem to be particularly good at calling neutral variants neutral compared to other gold standard methods, and we hope to further develop this tool and further release it to the public. So we already have a slightly older version available on this GitHub QR code here, which you can scan, but we should have the fully up-to-date version available before the start of the ISMB ECCB conference in just over a week's time. And finally, I would like to thank all of our funders for making all of this work possible. Thank you everyone for listening.